Go.
Hello again, peoples. Today's topic is about the electromagnetic spectrum. Now, first thing you have to understand is that this whole topic involves the idea of something called waves. You've just seen an example of that with a piece of string I had tied across the room here. Okay, you saw that when I disrupted the string, that the energy that I put into the string was then transferred across the room to the other side. Okay, and that's the whole basis behind waves. You cause a disturbance somewhere, and the energy of that disturbance is then taken from where it originates to some other place. So waves are an idea of transferring energy from one place to another. Now, the type of wave that I demonstrated there is a special type of wave called a transverse wave. And that means that the disturbance is at 90 degrees to the angle with which the wave actually travels. So I caused an up-down disturbance, but the wave moved at 90 degrees to the right as you see it. Okay? So that's the idea behind a transverse wave. Now, the electromagnetic spectrum really talks about the 7 different types of light that are all around us. Okay? And on this diagram here, you can see the 7 listed in order from left to right. Okay, and we'll go through a bit of the details. On the left here, we have radio, microwave, infrared, next to that visible light, which you know as the red, orange, yellow, green, blue, indigo and violet, that's detectable by the human eye. That's over here. Then we have ultraviolet or UV, X-rays and gamma rays on the right there. Okay, so in the exam, you are often asked to fill in the missing spaces, which means you need to know the order of the electromagnetic waves. Okay, right? One of the ways that I actually remember them is to use this saying. Radio, right, or real. Men in vests use X-rated games. Okay? You can come up with your own version if you want. Just keep it nice and tidy and safe. Okay. Now, over here, these numbers here in standard form. These numbers here represent what you see happening to this red wave that's going on here. As you go from left to right, from radio across to gamma rays, you notice something that changes. The waves are more bunched up. Now, the term we give that is this one, the wavelength. Now, there is a short way of representing the wavelength, and often you'll find that this Greek symbol, okay, is used to represent the wavelength. It's pronounced as lambda, but that's just me showing off. Okay, now what do these numbers mean? Well, the wavelength of a wave is the distance between 2 peaks, okay, of a wave, right? So this is lambda, the wavelength. And as you can see, these numbers here in standard form, as you go from left to right in that order, they actually get smaller. The little number in the top right, that negative number, means it's a number that's getting smaller. And the bigger the index, the bigger that number, the more negative it becomes, the smaller the wavelength. So lambda, the wavelength gets smaller from radio waves all the way across to gamma. Okay. Now, what else do you need to know about these types of waves? Well, you need to know something about this one, the frequency, often written as F. Now, frequency is measured in these units called hertz, capital H, little z for short. Okay, named after the famous fella all them years ago who actually investigated radio waves. Okay, but you'll notice these numbers again in standard form. There is no negative in these numbers in the index. They're all positive numbers, and these numbers are getting bigger. So what is happening here is it's saying as you go from radio waves across to gamma, the frequency gets higher, gets greater. Okay? So as you go from left to right, really, there is more energy in the waves. Okay? And as you go across, because the energy is increasing, as you get past visible light, you start getting towards a range of types of light, ultraviolet, X-rays, gamma rays, which are said to be so dangerous, we give them a term. We call these ionizing types of light or ionizing waves, okay? Because of the energy that's contained, okay? So, you've got the order, you know something about their properties in terms of the wavelength and their frequency. Now, the one thing they do have in common, boys and girls, and you'll often be asked this, is what do they have in common? Well, they're all generated by, do you remember what we call this type of wave? Where the disturbance is at 90 degrees to the angle with which the wave moves at? That's right, they're all transverse waves. Okay? And they have one more thing in common, boys and girls. They all travel with the same wave speed. Okay? Now, how do you relate the wave speed? Right, so there is a link between the speed of a wave to these two quantities here, the wavelength and the frequency. Come to the board, I will explain. Okay, now in your exam you will be given a formula sheet or an equation which tells you the link between the wave speed, the frequency and the wavelength. Now remember, the wavelength was given that symbol. I'll just write it down again, the wavelength. The frequency is given that symbol. Now on the data sheet, the wave speed is given this, okay? V, okay? And that's the wave speed, okay? Now, this formula, the connection between all these three, only works if you get the units right. Unfortunately, you are not given the units in the exam. You have to learn those, okay? Because you get extra brownie points for being able to do that. So, this formula only works if wavelength is converted into meters. Frequency has to be in hertz, and wave speed was then in meters per second. Okay? And the link is simply this. V equals F lambda. Okay? That means the frequency multiplied by the wavelength will give you the wave speed. Some people, in some questions, will ask you, give you two of these terms and ask you to work out the unknown. The way to do that is to use one of these triangle boxes where the terms go in. Because these two, the F and lambda, the frequency and the wavelength, are basically multiplied with each other. They belong in the two boxes down here. The things that are multiplied together go down here. Anything above here is the other missing one. So here we have the wave speed. Okay? And that simply means divide. Okay? So, you may be asked to rearrange the formula. For example, you might be given the wave speed and you'll be given the frequency and you're asked to work out the wavelength. Well, in this case, you have to make the wavelength the subject. In other words, you want lambda on its own. Okay? On the left of the equal sign. So let's cover up lambda here. And what we're left is velocity or wave speed above or on top of the frequency. Well, that's simply on top of that. That means to work out the wavelength, you need the wave speed divided by the wave frequency. Okay? And similarly, if you are asked to work out the frequency, you put it on its own, you come back to the triangle, you cover it up, and you are left with the wave speed over the wavelength. That is the thing. One more thing. For the higher papers, the tricky bit is they will often give you wave frequencies using some other forms of units of frequency or some other forms of units of wavelength. And you need to know something about these. For example, in frequency, you might be used to the word giga, or capital G for short. Now, giga in maths is simply this standard form. 1 times 10 to the power 9. That's 1 with 9 zeros after it. You might be given mega or capital M, such as megahertz, MHz. That is a million, or in standard form, 1 times 10 to the 6. And then the other one is kilo, or K. And that is 1,000, which in standard form is 1 times 10 to the 3. Okay? The other one I said was the wavelength. Okay? Now, if you remember the electromagnetic spectrum there, those numbers in standard form for wavelengths got very small. They were negative. And that's because sometimes you can get these mathematical terms. You might get milli, which is little m, not capital. And milli means 1 times 10 to the minus 3. You might get micro. Micro is that symbol, but it means 1 times 10 to the minus 6. Okay, or 1 billionth of a meter. Okay, and in the case of visible light and beyond, we have this one called nano, little n, and that is 1 billionth, or otherwise 1 times 10 to the minus 9. Okay, so that really concludes our talk on electromagnetic waves.